Hello students, welcome to MEC 1321 Statics. Today in this video I'm going to go over several example problems for chapter 2.1 through 2.3. We were unable to go over these in class, and so I want to give you guys as thorough a review of some of the examples from the book. Also in this video there will be a group activity problem that I'd like you guys to solve and bring to class during the next class. Just anticipate having to write out the solution to a problem at some point in this video. I can't anticipate how long this video will run, but I know it will be useful for you, particularly when you start doing your homework assignments. So let's go ahead and get started here. We're going to do example 2.1 from the book. That's going to be the first example. In this example, if we look at the diagram, we see that we have a hook that has two force vectors coming out of it. There's a force vector 1 and there is a force vector 2. And the question asks us to determine the magnitude and direction of the resultant force. Now, if you have watched the lecture video on the theory for 2.1 and 2.3, then you'll know that in order to determine the resultant vector, or a method to determine the resultant vector of two force vectors, is to use the Parallelogram Law or the triangle rule. And then also use the law of sines and law of cosines. So that is the approach that we're going to take to solving this problem. So the first thing we need to do when we set up a problem and we want to solve it is to list our knowns and our unknowns. The things that are given to us by the problem, and then the things that we need to find that the problem asks us to find. So one, knowns and unknowns. The things that we know the magnitude of the force vector 1 is equal to 100 newtons. We also know that the angle 1 for force vector 1 relative to the x-axis is 15 degrees. We also know the magnitude for force vector 2 is equal to 150 newtons, and the angle of force vector 2 relative to the y-axis is 10 degrees. And now what are the unknowns? The problem asks us to find the magnitude of the resultant force, so Fr, and also the direction of the resultant force. And in this case, we'll say the direction is theta r, where r is relative to the x-axis. Okay? So now that we've listed our knowns and our unknowns, we need to craft a free body diagram. So what we need to do is take the drawing that's given and idealize it and simplify it so that's easier for us to apply the engineering equations and principles. So let's go ahead and do step 2, which is creating a free body diagram. Now let me take a little bit of time here to kind of clear off some things. Clear it up a little bit. Okay. So with the free body diagram, the first thing we need to do is create our coordinate system so we can draw the x-axis and the y-axis. The second thing we need to do is remove the hook and just place the force vectors of interest. So we can put force vector 1 and force vector 2, and then their angles relative to the axes. And then we also, when we do a free body diagram, need to put the unknowns, the things that we do not know and we need to solve for. So let's go ahead. We can project and draw a line for the force resultant. We can draw the vector for the force resultant and the magnitude Fr, which we don't know. And then we can also draw the angle or the direction of force vector r, where theta r is the direction of the force vector r relative to the x-axis. Now, when we do that, we also notice that we don't know the angle between force r and force 1, right? We don't know that angle. And we can assume, and let's assume that the angle in between those two vectors is called gamma, okay? So now that we've drawn our free body diagram, we've put in both the knowns and the unknowns. We put in the arrows and the directional information. Now let's examine our free body diagram and see if we can extract any information from it by just looking at the idealized form. What we can do is, if we look at the problem, we notice that we have theta 1 that's relative to the x-axis, and we have theta 2 which is relative to the y-axis, but we do not have the angle that is in between. And we can call this the angle that is in between force vector 1 and force vector 2. Now, if we look at the problem in the coordinate system, we know that x and y, that between those two is 90 degrees because it's a right angle. And if we think that we have the total angle between x and y, and we have the two components angles theta 1 and theta 2, then we can do simple trig, and we'll find that 90 minus theta 2 minus theta 1 is equal to 65 degrees. And so we found the angle that is in between force vector 1 and force vector 2. So now that we've created this idealized free body diagram, and we've put in as much information as we could by just analyzing the free body diagram, let's go ahead and apply the parallelogram law in order to move towards solving this problem. So let's apply the parallelogram law. In the parallelogram law, the force vectors that we want to add together have to start at the same point. They have to have the same coincident point. So we can, in the free body diagram, we see that force vector 1 and 2 are already coincident. So we can draw them again, noting the coincident point. We can call this point O. And let me kind of clear this out again. Let me clear this out, and we can write it again. And then with the parallelogram, so we've drawn the force vector 1. We draw force vector 2. Okay, and let me clear this out here as well. Clear these things out. So we have force vector 1 and we have force vector 2. Now the parallelogram law states that the opposite side, or the opposite projection, is going to be equal to the magnitude and have the same direction as each other. So if we have a force vector 1 here, then we know that we can mirror it on the other side of the parallelogram, and it'll have the same direction, right? So we can draw it having that same direction. Also, we can do the same thing for force vector 2, where we can mirror it and project it, and it'll have the same direction and the same arrow. Once we've created these projections, then the point where they meet is called point P, the projection point. And the line that goes down the center of this parallelogram is going to be the direction of the resultant force vector. So now that we've created our parallelogram, what we want to do is we want to find the interior angles of the parallelogram. Now, it's important to note that because this is a parallelogram, and these sides are parallel and equal to each other, the force, the angle here, 65 degrees, which we've already found, is going to be mirrored on the other side where point P is. That's 65 degrees, right? So now that we know that it's mirrored from point O to point P, we also know that the other two corners are going to be mirrored. So they're going to have the same value. So what we can do is we can apply geometry in order to find those interior angles. We know that inside of a parallelogram, that the total sum of the angles of all the angles is going to be 360 degrees. So we can do simple algebra. We can create a simple equation which will allow us to find the interior angle of these two corners. So we know that there's 360 degrees total. We can subtract the 265 degrees that we have, and then we need to divide all of that by 2, because there are two angles that are still remaining. There's two corners that do not have an angle, and they're equal, so we can divide by 2. When we do that, we find that the value of the angle should be 115 degrees. So we can put 115 degrees on both of these corners, these opposite corners. So now that we've done that, we found the angular information inside of the parallelogram. Let's go ahead and apply the triangle rule. And the triangle rule will allow us to find the magnitude. So remember, the triangle rule uses the heads to tails approach, where you take one of the force vectors and you go head to tail with the other force vector. In the case of the triangle rules, in the case of the triangle rule I use here, I start with F1, where I start with F1, and the head of F1 meets, well, the tail of F1 meets with the head of F2, something like that, where the end, or the arrow for F1 meets with the start point for F2. And when I do that, I can project a line from that start point of F1 to the tip of F2, and that point is going to be point P. Okay? And so from point O to point P is going to be the direction of the resultant force vector. Okay? Now, if we look at this triangle and we compare it to the parallelogram law, we find that inside of the parallelogram law, we find that the angle between F1 and F2, when they're projected to each other, is 115 degrees, right? And if we look at our triangle rule, it is exactly half of the parallelogram, right? And so we find that we can take that 115 degrees and apply it directly in our triangle, okay? We also find, if we look at our free body diagram, that angle between F1 and FR, which we call gamma, appears within the triangle. So the angle between F1 and FR is gamma here. So now that we've done that, we have a certain amount of information about our triangle. We can use trigonometry. We can apply the laws of cosines and law of sines to try to help us find the magnitude and the angular information, okay? So, the law of cosines. Remember in the video, the law of cosines, we said that the side C is equal to the square root of a squared plus b squared minus 2ab cosine of c. Well, what we're going to do is we're going to replace those quantities a, b, c with the magnitudes of the force vector 1, 2, and force vector r. Okay? So we take our law of cosines and we find that the magnitude of the force resultant is equal to the square root F1 squared plus F2 squared minus 2 times F1 times F2 times the cosine of a certain angle, the opposite angle, which in this case is 115 degrees. So now, if we look at this law of cosines and we look at the equation, we know the magnitudes of F1 and F2 because those are givens, and we've also found the angle, which is 115 degrees. So we can directly solve for the magnitude of the force resultant using the law of cosines. And it's important to note that we took the time and we did all of these steps in order to find the information we needed to actually apply the equations. So we can't just immediately use the equations. We've got to find quantities that are used within the equations to find our unknowns. So now the next step is we need to find the direction of the force resultant. For that, we can use the law of sines. Remember in the law of sines where it is a over sine of a is equal to b over sine b, which is equal to c over sine of c. In this case, we're replacing, again, the a, b, c magnitudes and angles with the force 1, 2, and r magnitudes and angles. When we do that, when we replace them, we find that F2 divided by sine of gamma is equal to FR divided by sine of 115 degrees. And if we look at this problem, we know F2, we've just calculated FR, and we have our angle 115 degrees. And so we need to find that angle gamma, which is the angle between the force vector 1 and the resultant force vector. So we can simply take this equation and we can rearrange it and solve for gamma, where we move the like terms to one side of the equation, or the known terms to one side of the equation, and we do the sine inverse, and we'll find that gamma is equal to the sine inverse of F2 times sine of 115 divided by FR. And so now we have an equation and we can solve for the value of gamma. Now, let's very briefly scroll back to the top where our unknown is the angle theta r, where theta r is from the x-axis to the force resultant vector. Now we've just calculated the value gamma. So what we need to do is find theta r. And so we can simply do an equation and we'll find that theta r is equal to gamma plus theta 1. And so very simply, we can apply these equations. So we do the calculation for the magnitude of the force resultant. We find the force resultant is equal to 212.6 newtons. We do the law of sines and we find that gamma is equal to 39.8 degrees. And then using geometry, we find that theta r is equal to gamma plus 15 degrees, which is equal to 54.8 degrees. And this is how we solve these basic problems of adding force vectors together in order to determine the resultant. So let's go ahead and do another couple of problems. These we'll do a little bit quicker because I don't want this video to go on and on. So let's look at example 2.2. In this example, we have a linkage system, and it asks us to find the components of the force that is 600 degrees projected on axes U and on axes V. So we need to decompose this force vector 600 pounds into vectors along the U direction and along the V direction. Okay? So let's go ahead and do the first step, which is determining our knowns and our unknowns. Our known is the magnitude as well as the direction of the force resultant, which is 600 pounds. Our unknowns are the component forces, so force U and force V. So now that we've listed that, let's go ahead and try to idealize our problem. So let's go ahead and try to idealize this problem into a Freebody diagram. So let's start with that. The first thing we can do is we can remove the linkages because the linkages are not of interest, and we can find some point about which we will set as our origin. In this case, we can say at the linkage point between link A and B, we can say that is point O. So we have a point O here. Okay? We can put in our known, which is our force resultant, which is 600 pounds, and we can put in the unknowns. We can put in the unknown, which is directed along the axis U, and the unknown, which is directed along the axis V. Okay? And then we can put in the angular information that the problem gives us, which is along the projected direction U, in between U and V, there's an angle of 30 degrees. And then in between U and the direction of the force F, there is also 30 degrees. Okay? Now when we do that, we've created our Freebody diagram, right? Now what we need to do is look at our Freebody diagram and see what additional information we can obtain from it before we start applying our rules. In this case, we have the angle 30 and 30, but there's another angle that we do not know, which is the angle between F and the direction U. So what we can do is we know that if there is a straight line, that on one side of that straight line there is 180 degrees. Right? So we know that in total, if we go from this point to that point, there is 180 degrees. So from that assumption, we can do a quick calculation and see that 180 minus 2 times 30 degrees is going to give us 120 degrees. So this remaining angle here is 120 degrees. Now that we've done that, let's go ahead and try to apply our parallelogram law. In this case, we already know the directions of FU and FV. We just we just need to enclose the parallelogram such that we can start applying. We can move towards creating the triangle rule. So now that we've done that, with the parallelogram law, you start with determining the coincident point. In this case, in our free body diagram, we have a coincident point, and that's point O. And then we can draw in the things we know. In this case, FR, which is the resultant force, is already given. So we know the projection point P is going to be at the end of F, right? So now we just need to create the parallelogram, which is mirror the sides. So in this case, we're mirroring the FU, and in this case, we're mirroring the FV. And once we've mirrored them, we need to find those interior angles, okay? Now, when we've analyzed the free body diagram, we found that there's this angle of 120 degrees between F and FV. So we can take that information and put it directly into our parallelogram, okay? So we have the 30, we have the 30, we have the 120 degrees. We can put it inside of the parallelogram. Well, if we look at this 120 and this 30, we find that we have 150 degrees on this angle here, okay? And then there's 30 degrees here and 30 degrees there. And we can put in that information. We can kind of fill in those interior angles in the parallelogram. Now, once we've done that, and we have that interior angle information, we can use the triangle rule now, and we'll have the appropriate level of information. Okay? So with the triangle rule, again, what we do is we do a heads to tail approach, right? So we put our we create the triangle, we craft it using the information we're given. In this case, we can use the unknowns. So we can start with FU from the start point to the arrowhead, and then we can add the FV, which is the start of F. The head of FU is where FV starts, and then from that we can enclose our solution and project from the start point of FU to the head of the FV is our projected line F, right? And then we can use the information that we found from our free body diagram and from our parallelogram and fill in that interior angle information. Now that we have these interior angles, if we look at the triangle rule, the only unknowns we have are FU and FV, the magnitudes. And when we look at this, we can now start applying trigonometry. We can apply the law of sines. And we can replace the A, B, C magnitude and directions with F, FU, and FV and the associated angles. And from that, we'll find that F over sine of 30 is equal to FU over sine of 120, which is equal to FV over sine of 30. And simply, we take the law of sines, and we take the components, and we algebraically come up with the solution. So in the case of FU, we take these two parts of the equation, and we're able to solve for FU. In the case of FV, we can take these two parts of the equation, these two sides of the equation, and rearrange and solve for FV. And and the result is that FU is equal to 1039 pounds, and FV is equal to 600 pounds. And that's simply how we are to solve a problem. Now note that the first problem we solved was a problem where we were given two force vectors and asked to find the resultant. In this problem, we were given the resultant and asked to find the two force vectors. In this section of the book, those are the two types of questions that you will be asked. You'll either be given a force resultant and have to find the two components, or you'll be given the components and have to find the resultant. And it's going to be very important for you to be comfortable with doing either approach. Okay, now let's just do this one more example, and then I will show you the group or individual work that you need to turn in during our next course. This example is example 2.3. In this example, we have a pin that has two force vectors coming out of it, and it has an x and y coordinate system. This problem asks us to do something peculiar. It asks to find the magnitude of the force vector F, which is at an angle of 45 degrees relative to the y-axis, and the resultant force Fy that is directed along the y-axis. So let me kind of clear this stuff out here, okay? It asks for us to find the magnitude of F and find the resultant force Fy that's along the y-axis. If we look at the diagram, it doesn't show us an Fy. So what this problem is asking us to do is to actually find some force vector Fy, which is directly directed along the y-axis, okay? And so what we have to do is do the steps. First, we do our knowns and our unknowns, right? So we look at our diagram, we look at what's asked of us, and we can list our knowns and unknowns. In this case, we have this 200-pound force vector at 30 degrees relative to the x-axis. I'm going to call it force A, equal to 200 pounds, and the angle is 30 degrees. Then we have this this force vector F, which is unknown, and it has an angle relative to the y-axis of 45 degrees. And then we have this force vector Fy, which is directed along the y-axis. So our unknowns in this case are the magnitude F and Fy. So now that we've done that, we need to take our diagram and idealize it. So let's go ahead and create our free body diagram. We remove the pin, we remove the cables, and we replace everything with just the coordinate system and the vectors with their arrows indicating their direction. So we do that, we can do that. We have our x-axis and our y-axis. We draw our known Fa, which is at an angle of 30 degrees. We draw our unknown Fy, and we draw our unknown F, but the F is at an angle of 45 degrees. Then we examine our free body diagram and see what information we can extract from it, right? So we know that the angle between the x and y axis is 90 degrees, and we know that we can find the angle information, or the angle between Fa and Fy. So let's go ahead and do that. That angle will be 90 degrees minus 30 degrees is equal to 60 degrees, right? So the angle here that is in between vector Fy and Fa is 60 degrees. And this is useful information that we can use, okay? So now that we've done that, we've analyzed the free body diagram, let's start applying our rules. Let's apply the parallelogram law. Of course, to do that, we want to project the like angles. In this case, our force resultant, as the problem states, is Fy. So we're going to want to project Fa and F across the body, right? So we can take our free body diagram and we can start crafting those projections. So let me clean this up a little bit to make it a little bit easier to see and understand. Okay. So the first thing is to project those force vectors. They have the same magnitude and same direction, but they're just projected to enclose the parallelogram. So we have Fa over here, so let's go ahead and project it with the same direction, Fa. And then we have F here, so let's go ahead and project it as the same direction and magnitude, F. Now that we've done that, let's go ahead and start filling in the interior angular information. We know by looking at our free body diagram that the angle between Fa and Fy is 60 degrees. So let's put that information in here. This is 60 degrees. Now that we've done that, we know that the angle between F and Fy is 45 degrees, right? So if we look at the F the F that is projected and the Fy, we can say that this interior angle here is 45 degrees. And now that we've done that, we know that within a triangle there is 180 degrees. So we can find this additional angle here, which is the angle between F and Fa, by doing 180 degrees minus 60 minus 45 is equal to 75 degrees. So we found this third interior angle, okay? And so now that we found and filled in all this angular information inside the parallelogram, we can now transfer this information into our triangle rule, right? So with the triangle rule, again, we do a heads to tails approach of the components. So we can start with FA. And so we start with FA from point O to the head of FA. And then F goes from the head of FA to its own head. And then we have point P, and we have our point O. And our force resultant Fy goes from point O to point P. Now, if we look at this triangle, and we also look at our parallelogram, we know that the triangle is only 1/2, or kind of goes down the line from point O to point P of the parallelogram. So since we filled in this angular information, we can directly copy that information into our triangle rule. Now that we have our triangle, we can apply the trigonometry, in particular the law of sines, in order to find the magnitude of force F and force Y, those two unknowns that we need to solve for. So when we apply the law of sines, we find that FA is equal to sine of 45 degrees. FA divided by sine of 45 degrees is equal to F divided by sine of 60 degrees, which is equal to Fy divided by the sine of 75 degrees. So we're replacing the A, B, and C magnitudes and angles with the force magnitudes and the angles between those forces, okay? And now that we have this equation, we have our known angles, we have a known force A, which is 200 pounds, we can simply solve for F and Fy by taking parts of the law of sines. So in this case, if we want to solve for F, we take these two pieces, and if we want to solve for Fy, we take these two pieces. Rearrange and find our final solution. And then when we solve, we find that F is equal to 245 pounds and Fy is equal to 273 pounds. And that's how we solve this problem. Now it's interesting to note that every one of these problems is a little bit different. Each of these problems have different diagrams. There's different things that are asked of us, but ultimately we can apply those same general theorems in order to solve the problem. The procedures may be different. Sometimes we're using the law of cosines. Sometimes we're using the law of sines. But as long as we are vigorous in applying our methodology, we will be able to always find the correct solution. So it's important that you do some example problems and practice a little bit. So now this is the group activity that we should have did in class. Unfortunately, we didn't have enough time to do it. So what I want you guys to do is to take out a sheet of paper and attempt to do this problem. This problem is fundamental problem 2-3 in the book. So you should be able to see it in your book. Depending on the edition of the book, it may be a little bit different. So what you probably should do is just pause this screen, pause the video, and just write down and copy down this information, and then solve the problem. So in this fundamental problem, hold on a second. In this fundamental problem, we have a assembly of links that goes from C, A, and B, and there is a force of 400 pounds that's directed in the negative y direction from point A. And the problem asks us to resolve this force into components acting along member AB and along member AC, and determine the magnitudes of these components. So similar to the previous problem, you have a given direction, so the direction AB and the direction AC, where there are components, and you need to resolve the magnitudes of those components. So of course, the first thing you do is start with your knowns and unknowns. You know that the force resultant is 400 pounds and it's directed in the negative y direction. You're given some angular information of the value of f relative to the direction AB. You're also given some information that is the angle between AB and AC, which is just this 30 degrees. And you need to find the magnitude FAB, so from A to B, and FAC, from A to C, of the components. So go ahead and pull out a piece of paper, attempt to solve this problem, and after class, remind me after our next class, and I will post the video solution to this group activity. Okay, you guys have a wonderful day. I see the video's gone about 35 minutes, which is a bit long, but in the future, hopefully we won't have to create too many of these videos. Class time got tied up a little bit in going over Blackboard. We probably spent about 30 minutes on Blackboard, so it kind of evens out. So you guys go ahead and get to studying, start doing those mastering engineering problems, and come prepared for our next lecture.